myself Rakhi Kumari, Assistant Professor in the Department of Electronics and Communication Engineering, ABS Engineering College, Ghaziabad, affiliated to Dr. APJ Abdul Kalam Technical University, Lucknow. Today in the lecture series of Microwave and Radar Engineering, we are going to give the lecture or part 2 of the microwave measurement. I think already you have gone through the part 1 of the measurement of the microwave measurement, in which we have covered the topic like insertion loss measurement, and in the insertion loss measurement section we have completed attenuation loss measurement, attenuation measurement basically, reflected power measurement, and after that combining both we are able to get the insertion loss measurement. And in that particular section again we have done frequency measurement with the help of the two methods. First one is the slotted line method and the second one is the resonant cavity method, which is the direct method also. And in the last we have covered the measurement of the quality factor of a cavity resonator. So, continuing with that, we are going to measure the now measurement of dielectric constant of any device or any component. So, what is the dielectric? First of all, we was going through the measurement of the dielectric constant. First of all, we have know what is the dielectric constant and why it is so much significant in the case of a microwave measurement, microwave theory, or I can say microwave, that we are going to measure it. So, electromagnetic properties of a non-magnetic material or a medium can be completely specified by the terms such as permeability, conductivity and the dielectric constant. These are three important parameters on basis of which electromagnetic property of a non-magnetic material or a medium can be decided. Permeability, which is given by the mu, which is a symbol of having a symbol of mu, is a measure of the efficiency of transfer of magnetic force. So, conductivity, which is represented by sigma, is a measure of the efficiency of the transfer of electric charge, and dielectric constant, which is sometimes also called as the permittivity, is represented by epsilon and is a measure of the efficiency of transfer of electric force. And every one of you knows the significance of electric force in the case of a microwave. That is why the measurement of dielectric constant is important for us. Now, first of all, now before going to the measurement, let us look over the dielectric constant. The complex dielectric constant has a real and imaginary part, and it is given by epsilon is equal to epsilon naught within bracket epsilon dash minus j epsilon double dash. This is the dielectric constant in a free space or a vacuum. This is a fixed quantity. Epsilon dash is the ability of a particular dielectric to store energy, and this indicates the imaginary part, and epsilon double dash is a measure of dissipation of energy in a medium. So, this two parameters vary as per the dielectric which we have chosen, and the first one is the fixed parameter. Now, dielectric constant is also referred as the permittivity of the medium, and it is given by epsilon r. Epsilon is equal to epsilon r into epsilon naught, where epsilon r is the relative permittivity which is varies as per the medium which we are choosing, and epsilon naught is again a absolute permittivity which is a fixed, and it is a permittivity in a free space or a vacuum. So, relative permittivity is given by epsilon upon epsilon naught, that is equal to, of course, epsilon dash minus j epsilon double dash, and so if we take epsilon dash as common, it is equal to 1 minus j epsilon double dash upon epsilon dash, and it is called as the loss tangent, and it is given by tan del, and it is also gives the loss of a system. Now, the experimental setup for the measurement of the dielectric constant. First, as I have already told you that we use the microwave test bench for the measurement purpose in the case of a microwave, and the first part is the microwave source, and the second one is the, you have seen in the part 1, what is that, our attenuator. The pad basically here is the attenuator which is used to lower out the signal level. Now, frequency meter which is used to measure the frequency, slotted line and crystal detector, dielectric sample, short circuit, VSWR, SWR meter, or you are able to say VSWR, that means voltage standing wave ratio meter, because SWR is measured in the terms of electric field, current, but the most common one is the voltage. So, this is a general setup for the measurement of dielectric constant of a medium. Now, what we have to do? We will go through this process first. Guided wavelength is measured using the frequency meter. The thickness of the dielectric, the sample dielectric which is connected here is measured, and micrometer of the short circuit, where that means ki with the device which is used connected to the short circuit is again adjusted to the same value as the thickness of the dielectric, is adjusted so as to have the same value as the thickness of the dielectric which we have already measured in the step 2. Now, the fourth step is the exact position of the first and the second minima from the right hand side of the SWR meter is noted. So, what is the, for measuring the first and second minima, what we have to do? We have to move the slotted line and check the SWR meter. When the SWR meter shows the on the minima side, then we note the value of at the slotted section, and again we keep on moving the slotted section, and if again we are at the whatever value we are again achieving the minima is the second minima point. So, it is noted with the help of slotted section and the SWR. This is the fourth step. Now, the fifth step is that the short circuit is then removed. This short circuit is removed in the fifth step, and the dielectric sample is inserted into the aperture of the short circuit, and dielectric field short circuit on the SWR detector is then replaced, and the position of the first minima from the SWR detector is once again measured. First, with the short circuit we have measured the first and the second minima, and now we are measuring the first and second minima without the short circuit and dielectric field short circuit on the SWR. The shift in del S of the standing wave caused by the dielectric is now determined. If the thickness, dielectric thickness is d, because we have already said to measure the thickness of the dielectric, and short circuit is adjusted to same level. We calculate the quantity x which is given by the this formula. Lambda g is calculated with the help of our what, minima and the minima, two minima difference which we have already discussed in the frequency measurement, how to calculate the lambda g, that is the guided wavelength. Now, del S shift in the SWR meter due to first in the short circuit, second when the short circuit is removed, and the d is the thickness of the our dielectric. So, we are available with all the values. So, we are easily able to calculate the x. Now, comes the Robert Ann von Hippel is a scientist who related the x which is calculated here with v. V is what already known to you, that is the our wave number of the wavelength of the microwave radiation. So, he basically give a value of x with respect to v. This is the basically our plot, tan 2 pi v upon v as the function of x. So, this plot is taken, and from this plot whatever be the value of x, we are able to get the, if we have a value of x as 0.6, that means we are getting at this at the negative. So, we are able to get the value of tan 2 pi v upon v by this graph. This graph is very important for the calculation of the dielectric constant. And now, for the value of x measured, the value of v are known to you. So, now we can able to calculate the dielectric constant using this formula, because already we have lambda naught, and how to calculate lambda naught, you can get that from the frequency measurement topic which has been discussed in the part 1. I am not going to repeat that again, and lambda g is also from that, which is obtained by the getting the value of minimas, and lambda naught v value from here, and d is the thickness of the dielectric. So, now we are able to get the dielectric constant value. So, for getting the dielectric constant value, what we have to know first? You have to go through the frequency measurement topic again. Where we have discussed how to get the lambda naught and how to get the lambda g. So, now again the most important parameters in the case of a microwave, that is the scattering parameters. So, already in the unit 2 we have gone through the scattering term. The scattering terms plays a very important role in the case of a microwave measurement, because any device which is available with us, if we say a 2-port network, it is giving signal to 1 to 2, and if there is a mismatch, signal will be reflected back to 1. So, signal 1 to 2 is the okay, but 1 to 1 has to be in the lower side or should have a negative value, then only our device is said to be working properly. So, the calculation of our S11, S12, S21, S22 is very significant in the case of a microwave measurement, and this is done by two methods. First one is the by using network analyzer, and the second by measuring the amplitude and phase from the ports through the dual directional coupler. By second one method is the amplitude and the phase from the dual directional coupler. So, first one is the network analyzer. Network analyzer is a very common instrument which is used for measuring the S parameters of a particular device, any DUT, and means device under test. It is basically of the two type. First one is the scalar network analyzer, and the second one is the vector network analyzer. A scalar network analyzer provides only magnitude characteristic of the microwave device as a function of frequency. So, scalar, we already know the scalar means only magnitude, and vector means magnitude and direction both. So, when we talk about the scalar vector analyzer, that means it gives only the magnitude characteristic of the microwave devices as a function of frequency. And when we see a vector network analyzer, what it give? Can give the measure complex reflection or transmission characteristic of a microwave devices. The most commonly out of these two is of course vector network analyzer, and the principle of working of both the scalar network analyzer and the vector network analyzer are same. The basic principle of measurement is to generate an accurate reference signal and compare that with the test signal whose amplitude and phase are to be measured. So, in this case what we are going to do, we generate two type of signals, a reference signal and the test signal. Test signal should be from the device who is under test, that is DUT. Our device whose reflection coefficient or the transmission coefficient or the S parameters we want to calculate. And when we compare On the basis of that, we get able to get our S parameter value. So, basically what we do, this is the general setup of the inside the our network analyzer. Sweep signal generator, then comes the power divider. Power divided the signal to the power divider, divide the signal into first test signal and the second one is the reference signal. So, what we have, test signal is given to our DUT, device under test, whose parameter has to be measured, and the reference signal is sent to the length equalizer, because it will taken as the reference one for the comparison purpose. And in the harmonic frequency converted, our IF, intermediate frequency signals are generated, and when it is compared, we are able to get the our S parameter values. So, what we are discussed here, a sweep generator, what is going to do, it generates a signal and feeds a power divider or splitter, and that is convert the signal into two signals, a test signals and the reference signal. Test signal is fed into the DUT, the device under test is fed with the test signal, and the length equalizer is fed with the reference signal. The test and the reference signal are fed into the harmonic frequency converter to give the standard IF frequency, and the output of the harmonic frequency converter is then used to determine the amplitude and the phase of the test signal, which is further calculated to give our S parameter value. Now comes the another method for the measurement of the S parameter of any device under test, that is by the dual directional coupler. So, this is the two setup for getting the S parameter by the dual directional coupler. So, what is the basic principle behind this? The S parameter of a two port network, it is a two port network DUT, can be obtained by measuring the amplitude and phase from the ports through which dual directional coupler, as shown in figure, by interchanging the RF signal source and the load position. So, what is the basic thing here? We have taken the DUT is same in both the setup, dual directional coupler, DC stand for directional coupler. Both the device setup does not change, but what is the change here in the two setup? In the first setup, we are providing the RF signal source, and in the second and at the end we have a load. But in the second setup, what we are doing? We are interchanging the RF signal source and the load positions. So, what we are doing? Load comes to this position and the RF signal comes to this position, and in both the cases, what is calculated? V1, V2, V3, V4 are calculated in all the case, and when these values are available with us, we can use the formula to get the value of our S parameter. Already I have told you, for the two port network we have S11, S12, S21 and S22. S11 return loss, S12 insertion loss, same thing here. So, from the first setup we are able to get the value of S11, which is equal to V2 upon V1 within bracket, if we want the direction also, phi 2 minus phi 1, and S21 should be equal to V3 upon V1 within bracket phi 3 minus phi 1. This value S11 and S21 value can be calculated from the first setup. This is the setup 1 and this is the setup 2. Setup 2 is used for calculate the S22 and S12 value. So, for getting the setup 2, we are just changing the position of RF signal and the load, and by changing the position of RF signal and the load, again we are getting the values of V1, V2, V3 and V4, and which will be further used to calculate the S22 and S12. S22 will be equal to V3 upon V4 within bracket phi 3 minus phi 4, and S12 is equal to V2 upon V4 within bracket phi 2 minus phi 4. So, in this way we are able to calculate the S parameters of any device which is assigned to us for testing purpose. Now comes the measurement of noise factor. So, noise factor is basically what? Noise factor, so before going to the noise factor, what is the noise here? Because noise in all general cases we know it is an unwanted signal which come inside any device and disrupt the original signal performance. So, it has to be avoided in any device, in any communication system, not particularly in analog, digital, microwave or any. Noise has to be avoided in any device because it always disrupt the signals of a actual signal performance. So, and it has to be calculated so that from the original output which we will obtain, if we know the noise level, we are able to get our original signal back. The noise factor is defined as the ratio of the actual output noise power of the device to the noise power that would be available if the device were perfect without itself contributing any noise. So, what is the noise ratio factor? Noise factor is the ratio of actual output noise power of the device to the noise power that will be available if we are saying that the device is not contributing any noise. Now, the noise figure is a noise factor expressed in decibel and it is equal to F is equal to 10 log to the base 10 input signal to the noise ratio, output signal to the noise ratio. So, now comes the setup for the measurement of the noise factor. Initially, the noise output from the device in the test is noted connecting its input to the match termination. So, initial noise output from the device under test is noted down connecting its input to the match termination, and then the input of the device is connected to the standard noise source along with a pad. So, this is basically a setup for the second case. Setup, we can say setup 2, which is shown here. In the first case, what is the DUT, whose noise has to be noted down, noise output has to be, in the noise output from the device and is noted, noise output is noted with the help of a power meter, and at the input we have a match termination. And power is noted down, which is maybe P here. And the setup 2, what is done? This match termination is removed and our device under test is connected to a standard noise source with a pad, which is our attenuator, so as to lower down the signal level. So, this pad attenuator is adjusted until the noise output of the device is double. So, this one is adjusted until the noise output of the device, that means here the output is doubled. The noise factor of the device is then equal to the noise output from the attenuator, and from that the noise factor on the device is then equal to that of the noise output from the attenuator. So, how we will able to calculate? I am going to repeat it again. First, we are going to have a DUT, power and a match termination, so that device is perfectly okay. And now, this match termination is removed and the noise source and a attenuator is connected, and this attenuator is adjusted till the noise output of the device is doubled. Originally, we have some power or it is double. The noise factor of the device is then equal to that of the noise output from the attenuator. So, here comes the end of the noise factor of the device, our S parameter calculations. So, in this section what we have covered? We have covered the dielectric constant measurement, scattering parameters measurement and the noise factor measurement. So, for the next part of the microwave measurement, we will have in the next lecture. Thank you.